So we started from material behavior. Okay. So three types of material we commonly use. One is the concrete, masonry and steel. So these three types of material behaviors now you understand. You can plot the stress strain curve. That is basically the constitutive law of the material. Then from there we work on section behavior. So material behavior we represent in stress versus strain. Section behavior we represented M versus phi. Then we represented member behavior we obtained, and member behavior was either Q versus delta or M versus theta. And once we obtain the member behavior, we can get the structural behavior. Structural behavior we obtain VB versus delta rho. Okay, so for any building, subjected to some distribution of lateral loads, you can estimate the deformed shape, okay, and variation of this deformed shape with wedge shape. Something like this you can get. Okay. So up till this point we have covered, and this we call capacity curve of the structure. And what is this capacity curve giving us? The capacity curve is giving us stiffness, strength and ductility. It is signature of the structure. For one particular structure, we will get one capacity curve. Okay. This is representing behavior of the structure. The procedure which we have used for manual calculation, we have made some assumptions. One major assumption was the location of points of contraflexion. We have assumed, but in reality, the location of points of contraflexion will not be what we have assumed. It may be different. Okay. So for real structures, what we can do is what we call pushover analysis. Okay. This is also incremental nonlinear analysis. Okay. So the same problem we will subject it to an arbitrary lateral load, but the pattern of this arbitrary lateral load is predefined. Okay. So predefined pattern and arbitrary value of lateral. Okay. This is Qi, and the total force is base shear, and under this it will have some displacements delta 4, which is also equal to delta roof. So if I want to perform an accurate analysis of this structure, what I have to do? You are familiar with the matrix method, matrix analysis method. So you can make a matrix model of this, okay, and perform the analysis. For that you don't need assumption of points of contact. Okay, you can perform an analysis. There is only one limitation of the method which you know so far. What is the limitation of that method? That it is linear elastic analysis. So what you have learned so far, it is a linear elastic. So you can make a matrix of the whole structure, you can develop the load vector, and you can solve this equation. You can solve this equation, okay, and this equation gives you a relationship between base shear and delta roof, which is linear. Okay, you can increase Q by any proportion, the delta will also increase in the same proportion. That's meant by the linear relationship between the force and the displacement. This method will do. This method so far does not take into account the nonlinear behavior of the structure. Now, this nonlinearity in load displacement behavior of the structure. Why this nonlinearity comes? This nonlinearity comes because of two reasons. One is what we call geometric nonlinearity. Okay, geometric nonlinearity, it is due to P delta effects. Okay, and coupling between different actions. Okay, within a member, what are the different actions? Axial force, bending, okay, and shear and torsion. Okay, so when we developed the stiffness matrix, we considered the shear behavior, axial behavior, flexural behavior, and torsion behavior independent of each other. But actually it does not happen. There is a coupling. Okay, so for example, when we developed this stiffness matrix of this member, okay, and we considered that we applied an axial force and we considered that the axial action is independent of the bending action. If I give a unit rotation here, then there is no interaction between this bending and axial action. Okay. So when I gave a unit rotation here, there was no change in the axial force, or no axial force was required. But in reality, what will happen? When you will give this bending, actually the length of this curve shape of the beam is longer than the straight line, isn't it? The length of the curve is more than the length of the straight line between the same points. So what will happen? Because of this curved line, actually there will be a movement here. There will be a movement along the axial degree of freedom, and you have to keep the displacement along the axial degree of freedom 0. That is by the definition of the stimulus matrix. So by the definition of stimulus matrix, you have to give only unit rotation, keeping all other displacements 0. Okay. So to keep it 0, what you have to do? You have to apply a force in this direction. So this interaction will occur when we have not infinitely small deformations, when the deformations are finite. So whenever we have finite deformations, this will arise. Okay, and in addition to P delta effect, we have P small delta effect also. And I explained you the difference between P capital delta and P small delta. P capital delta is due to the displacement at the end. Okay, effect of axial force due to displacement at the end. So when this end is moving from here to here, let us say, then due to that additional moments will generate. That is P capital delta. But even when this is not moving, let us say when I have given a unit rotation, even then you can see at any point here there is a lever arm due to the deformed shape of the magnet. Okay. So due to that also additional moments will arise, and that is called P delta. So this is P small delta, this is P capital delta. So both these effects cause additional moments in the structure, and due to that the behavior does not remain linear. Why it does not remain linear? Because effect of these moments depends upon the displacement, the delta itself. So in other words, the stiffness is a function of displacement. Stiffness is no more constant. Okay, and this relationship which we have obtained here, okay, this will not be a straight line. Okay, and this analysis which gives us this straight line behavior, this we call first order, that means linear elastic analysis. So in this first order linear elastic analysis, we have neither considered geometric nonlinearity nor we have considered yielding. Okay. Suppose I consider geometric nonlinearity, P delta effects. What will happen to this curve? You have already seen. What does P delta do? It reduces. Okay, and that reduces the force registered at a given displacement. And how much reduction will be there, that also depends upon the displacement. Okay, so the behavior will be something like this. And then there will be instability, buckling will occur at some value of displacement, and after that it will become unstable. Okay, this is what we call second order. It is no more linear, so but it is elastic, still elastic. Behavior of analysis. Here we have considered only geometric nonlinearity, and this is our what we call elastic stability, instability. So still the material has not yielded just because of presence of vertical load and lateral displacement. The behavior is non-linear, and after certain displacement and depending upon how much vertical load we are applying, the whole building will become unstable. So there is certain gravity load, dead load and live load already acting on the building, and then I have applied these lateral forces. So if the displacement lateral force goes on increasing, the displacement will go on increasing, and so the P delta effect. And there can be a situation where the moments due to P delta effect will be so large, okay, that it will no more be in equilibrium. Okay. Or you have to reduce the lateral force to keep it in equilibrium. That is instability. So this is the nonlinearity in the behavior of the structure, which we are getting because of only the second order effects, which are due to finite deformation of the structure. Okay. Earlier we have assumed very small deformations in the structure, so the deformed shape was not causing any effect. Here we take that deformed shape into account. The deformations are finite, and due to that we are getting the nonlinearity.
So why its name is second order elastic?
Sorry?
Why its name is second order elastic?
Okay, what do we mean by elastic and inelastic? Elastic and inelastic comes from material behavior. When we say material behavior is elastic,
When it limits the loading and unloading part.
when the loading and unloading are the same, so there it is elastic. Okay, and what is meant by inelastic? When there is permanent deformation. Okay, so still the material has not gone into a range in which there is a permanent displacement. Okay, here even if you remove it from here, it will come back to the original position. It will follow this path, but it will come back to the original position. So path is non-linear, but it will come back to the original position. Yes.
But sir, after that T point, after it will achieve the decline path.
So even if you remove all the loads from here, you remove the loads, vertical load as well as it will come back. Why? It will come back to the original position.
Which is that material?
It is any material. Let us say steel, because material has not yet yielded. Okay, it has only buckled. You have seen, we have done that experiment, buckling experiment in your BTech graduation also. You take a strip, apply a load, it will buckle, but when you remove it, it is not permanently buckled. It will come back to the original position.
It's a compression. Here we are applying pusher.
So how the buckling? Let's do this also. You visualize a strip like this, which is subjected to this load, and then you apply a load, you deform it here. So how you will deform? By applying this lateral load only. This is P and this is Q. Sorry. Okay. If you deform it further, what will happen? It will collapse. You agree? But suppose you don't take it up to the collapse. From here, you remove the load. What is going to happen? You remove both P and Q. What is going to happen? It will come back to the original position. There is no yielding, no plastic hinge has formed yet. Okay. So that's why this behavior is still elastic. But there is a nonlinearity. That nonlinearity is arising because of geometric reasons. And the major contribution in this geometric reason is P delta effect. Okay. So this is one source of nonlinearity. The other source of nonlinearity comes from material yielding. Again, with material nonlinearity also, we can perform two analyses. One is first order analysis in first order inelastic analysis, what will happen? Some yielding will occur and you may get this type of behavior. This is first order inelastic. First order inelastic. So here yielding is occurring, and after yielding it is not taking any more additional load, but it continues to deform and then it finally breaks. Okay, but what will happen? The geometric nonlinearity and material nonlinearity both will act together. Okay, and what we have here is second order inelastic. So in addition to material nonlinearity, material yielding, we are considering p delta effects and geometric nonlinearity also. Okay, and what will happen in that condition? You know, we have done that already. Due to p delta effects, what happens? The yield force also reduces, and then what happens? It goes like this. Okay, the effect of p delta goes on increasing. The effect of p delta is increasing with the displacement. You have seen it is like as if we have rotated the whole q delta curve of base shear versus delta roof curve by some angle. Okay, so here the effect of p delta is less, here the effect of p delta is more. So this is second order inelastic. Okay, and this is actually the behavior which we are looking for, where we have to consider the effect of geometric as well as material nonlinearity. So the analysis which we have to carry out is second order inelastic behavior. Means we have to consider the material nonlinearity by providing suitable hinges in our model and also considering the p delta effects. Okay, so when you are performing analysis using a software, you have to provide potential plastic hinge at the locations where you are expecting the yielding to occur, and do not forget to choose p delta or large displacement analysis. Okay, otherwise it will be first order inelastic behavior. If you are not considering, if you are not choosing the option of large displacement or p delta effect, then it will be first order inelastic analysis. Okay, so in addition to that, you have to also consider the p delta effects there, then it will be second order analysis, and this is closer to the reality. Okay, the behavior of the structure is going to be close to this. It is definitely not the first one, that is very ideal behavior, but most of our studies focus on the first behavior. Okay, so you can see that the actual response is significantly reduced, the capacity is significantly reduced because of the geometric and material nonlinearity. In our analysis, we should take into account both. So let's go back to that problem. We were trying to obtain the pushover curve of this building. Okay, how we can obtain? The simplest method for obtaining the capacity curve of a structure let us apply the lateral forces in a particular pattern. So this pattern of Q, it should be close to that occurring during earthquake. Okay. So what pattern will be occurring during earthquake? How you can obtain that? The distribution of the lateral force along the height. So we are not estimating here the actual force. We are just estimating the pattern. How this will vary along the height. How we can get that? During earthquake? During earthquake it is subjected to ground motion and it is vibrating like this. How we can get the distribution of the forces? Motion. Which motion? So most of the contribution is coming from the fundamental. Okay. And here we can consider it proportional to fundamental. Okay, so this Q is proportional to first. Okay, here we are considering single mode. That's why this is also called single mode method. Okay. We are considering the peak value of these loads, okay, and the load is increased gradually, very slowly. We are not considering dynamic effects. That's why this is also called static analysis. And we call it nonlinear static. Okay, or pushover. Because we are not considering the dynamic characteristics of the applied load. We are considering this load monotonically increasing in one direction. We are not considering any variation, okay, with time, any reversal of these loads. In reality, what is happening when it is subjected to earthquake force? Earthquake motion at the base, the building is vibrating, and when the building is vibrating, actually the effective force which is acting on that, it is changing instantaneously with time. And not only it is changing, it's reversing its direction. So that variation we are not considering. We are just considering the monotonically increasing forces, okay, with slow rate of increase. So that's why we call it static. So I can represent the total force as I discussed earlier by base shear and the displacement by the largest displacement which will occur at the roof. Okay, and this relationship between base shear and delta roof this I am interested in. And if I perform my normal analysis, which is first order elastic analysis. So first order elastic analysis is going to give me a straight line, as we discussed this one. You can consider P delta effects also. Okay. So because the P is coming here due to gravity, and also when you are pushing it, one side columns will be subjected to compression, another side columns will be subjected to tension. So axial force will also come because of lateral force. Okay. So you take effect of both also into account. Okay. You will get a slightly non-linear behavior, including P delta. Okay, but that will be elastic. Now, how to determine that whether any hinge has formed here or not, any yielding in the material has taken place or not? Because this force which I have applied, it is arbitrary. The pattern is proportional to the first mode, but you know, mode shape doesn't give any value, absolute value. You multiply mode shape by any factor, still it remains the same mode shape. So you can have any value with the same variation, same pattern. So actual value of VB is not known. So I want to know that whatever value I have applied, under that value, whether any plastic hinge has formed or not. How I can get that? To calculate DCR at every potential hinge location. What are the potential plastic hinge locations in this building? Can you tell me? What are the potential locations where plastic hinge can form? Both ends of the beam and base of the column. Are these only potential hinge locations? Or there are some other? Also? So all these joints. So beams and columns near the joints. All these locations are plastic potential hinge locations, where there is a possibility of formation of the plastic hinge. Okay. Now, suppose I don't know exactly where there is a possibility of plastic hinge location. Okay. I can choose more locations where actually plastic hinge may not form, but I can choose some location when I am in doubt. So if I am choosing larger number of locations than required, actually I have to do more calculation, that's it. But I am not making any error. If plastic hinge is not forming at any place, it will not form. Even if I check it, it is not going to form. Only thing is that my effort in checking will increase. So if you know the potential hinge locations precisely, your effort will be reduced. But when you are in doubt, check more locations. So any location, if you are having any doubt, better calculate DCR there also. Do not leave it. Okay. So if you are considering larger number of locations, it will not affect your results. Only thing is your calculations will be more. You have to do more calculations. Okay. So after doing the DCR, wherever the DCR is greater than 1, those are the locations where plastic hinges will form at that point. You are so I can determine where the first plastic hinge is forming. We have already used that procedure. So to obtain that value of the base shear where the first plastic hinge is forming, what do? We take the larger DCR max, out of all these locations and equate that equal to 1. So wherever the maximum DCR is occurring, that is giving me the location of first plastic hinge. Let's say first plastic hinge is forming here. So here the DCR will be maximum, and that DCR I will equate equal to 1. So corresponding to DCR equal to 1, I will get certain value of base shear. Okay, because demand depends upon base shear. Demand is in terms of base shear. Capacity depends on the cross section. So when I will equate DCR equal to 1, and you have seen in the numerical examples also, you will get this first value of base shear. And once this is known, and the corresponding displacement also, you will know. Okay. After formation of this plastic hinge, here, what will happen to your structure? Will it remain same? Stiffness of this will remain same? No. What is going to happen? So the stiffness will be reduced. So you can again develop a model of your structure with this plastic hinge being modeled as a release. Okay, so you can release the moment at this plastic hinge, and you can develop a model again. And when you develop that model again and perform this first order elastic analysis, its behavior will be given by a line. Okay, the slope of this line is going to be less than the first one. So stiffness of the structure is going to reduce. Okay, you can repeat the same process again, perform an analysis, but do not forget that some forces in the members were already acting. So it is an incremental analysis. Okay, so consider that force also, like we have done when we were doing the analysis by hand in simple calculation. What we have done, we have calculated the remaining capacity. Okay, so either you consider the remaining capacity, DCR with remaining capacity, or consider the full force from the first increment and the second increment. Okay, and that you compare with the capacity. So calculate the new DCR, equate the maximum DCR equal to 1, that will give you the second hinge location, which will occur, let us say here, the second hinge is formed. It can happen anywhere, depending on how much capacity you have provided. Okay, so you will get the second location, and after that the behavior will further change, and it will be given by another line. Okay, so here what we are doing, we are performing first order elastic analysis only. Okay, so we are doing piecewise linear. Linear is always first order. Even if it is elastic and we have considered P delta effect, it will be no more linear. Okay, so piecewise linear elastic analysis. Okay, I can consider P delta effects as well. What will be the effect of P delta if I consider P delta also? These points will shift like that. So this is what I will get from second order. Okay, the demand will increase because additional moment in beams and columns will occur due to P delta effect. So the demand is going to increase, and as a result, at a lower value of V1 dash and V2 dash, I will get yielding at these locations, at these hinges. If I continue this, I will get a curve like this. This curve which I get by joining these points, this curve we can call capacity curve of the structure, building in this case. Okay. And we have obtained this by piecewise analysis. Okay. If you consider the P delta effects, actually we have considered it linear, but actually this is also non-linear. You know, a small piece is also non-linear. Okay. So if you are doing this piecewise analysis, so size of these pieces or steps has to be small. And you have to keep record of each joint, each potential hinge location in each step. As soon as the hinge forms at one step, you have to change the structure. So you have to do a lot of bookkeeping. Okay, but using simple software which provides you linear analysis, including P delta effects, you can use that to develop this capacity. You don't need any special software. So is this possible here?
This capacity curve is formed for the material plus provided.
Both, because we have considered P delta effects also here. So this includes both the material as well as geometric knowledge. Okay, and we are using our usual software for the analysis, okay? Usual method of analysis. Okay, only thing is we have to do a lot of bookkeeping. We have to keep track of forces. So this is incremental analysis. So at any step, the forces and displacements will be obtained by summing up the forces and stresses, forces and displacement which we have obtained in all the previous steps. So we have to sum up this. Then we will get the forces and displacement at every step. Okay.
So
Yes.
step size should be smaller. Step size.
Okay. Step size should be so small that in between that you can represent it by linear. So that means in that step size no additional hinge should take place. That is one thing. Secondly, sorry, the effect of P delta should also be small.
Steps to when first plastic hinge from there to second step plastic, that is a step.
Right. But suppose this step is much larger, then what will happen? The stiffness which you have assumed it to be constant, that stiffness will not be constant. Due to P delta effect, the stiffness will reduce. So you have to have some steps in between also. Okay. So that between two hinges also you have to have some steps to take into account the P delta effect. Because when the force is increasing, okay, the axial force is also changing. When lateral force or the base shear is increasing, the axial force is also changing. And due to that axial force, the P delta effects are changing. And due to that, the effective stiffness is changing. So if this, suppose plastic hinges are forming quickly one after the other, then you can go ahead with that. But suppose there is large gap between two plastic hinges, then the stiffness between those two plastic hinges cannot be taken as constant. That stiffness will also change. Okay. So this is how you can use a conventional software. But when you are performing P delta analysis in SAP or ETAPS or any other software, actually it does not work like this. Okay. So there is a method, there are rather a number of methods of solution of nonlinear analysis problem. Okay, so our conventional linear analysis, we have some KE, E I am representing for elastic, so KE into delta is equal to P. This is our first order elastic analysis problem. You are all familiar with this. P is equal to K delta. Yes.
How do you ensure that you in elastic range? Because we are saying first order elastic analysis.
So this is not the one which we are looking for. I am just to represent the difference between the two. That what is the difference between elastic and inelastic, linear and nonlinear. That's why I am writing this equation. So I am going to modify this equation to represent the case which we are trying to solve. We are not trying to solve this problem. This is the simpler case, and I have used, actually for lateral load I have used Q, so I will continue with the same notation. Okay. So this is the problem whose solution you know. Okay. You know how to solve this. So how to solve these equations? Yeah, matrix. These equations are written in the form of matrix. Do you know some solution method to this? Gauss elimination, okay, Cholesky factorization. Some of the method you will use to solve these equations. Okay. Now what happens in case of nonlinear relationship? This is the general relationship between Q and L. Okay. So here this equation cannot represent. So what we do is, suppose I take one point here and another point here, and this I represent by dq, a small increment in Q. Okay. And this is Qi minus 1, this is Qi, and the correspondingly this is delta I minus 1, and this is delta I, and in between this step is dq. Okay. So here the relationship is going to be some Ke plus some other matrix, let me call it K bar, okay, into d delta is equal to dq. What is this K bar? This is nonlinearity matrix. Generally, it is causing reduction in the stiffness, whether it is P delta effect, dramatic nonlinearity, or material nonlinearity. This is causing reduction in the stiffness. So this K bar is usually negative. Okay, you will find that this is negative. It will reduce. So original stiffness was this. Okay, this stiffness you can see it has been reduced. Okay, and this we call tangential stiffness. Tangential stiffness which we are obtaining here, and this stiffness is obtained from the elastic stiffness minus some terms. Okay, I have shown it plus because this is a negative matrix. This may be due to geometric nonlinearity. This may be due to material non-linearity or both. Kg and Km we can add. Yes.
For determination of KE, you are taking the tangent at first point, QI minus 1.
Right.
And also for KE, you are also taking the tangent at that point. So at the one point, the slope will be equal for any tangent. So why there?
KE is this. Okay. And KT is this. So this is tangent here. Okay. It's not same as KE.
KE is the tangent, K bar is the tangent which is passing through initial point and last point.
KE is the initial stiffness.
Yes, initial and
KE is the tangential stiffness at ith increment, ith step. So at any step I, or rather I minus 1 I should say. So I minus 1, this is the tangential stiffness.
KT is the stiffness at the point where QI minus 1 we will draw a tangent, that will be KT, and K is the initial slope from 0 to
At the origin.
original. That is
At the origin.
from 0 to
K is at the origin. Okay. So we can see that this Kg and Km, these go on modifying with displacement. Ke will remain constant, but value of Kg and Km will go on changing. That will depend on this displacement. How much displacement has taken place here? If I take here, you can see that the tangential stiffness is changing. So this KT, this is also a function of delta I minus 1, and Kg and Km, these are also function of delta I minus 1. This depends on the displacement. How this depends on the displacement? P delta effect. Does it depend upon the displacement? Material non-linearity. Does it depend on displacement? Because displacement will give you the strain. Okay, and strain will decide how much yielding has occurred in my hand. So both these depends on the displacement. So you can see that these go on changing. So how to solve these equations? Okay, where this KT is a function of delta itself.
So what is Kg and Km?
Kg and Km are the additional matrices due to geometric and material non-linearity. These are usually negative matrices. So these are reducing the stiffness. How we can develop Kg and Km? Okay. How to develop Kg? I taught you in the last semester, some of you call minus P by L. Okay. So you remember, due to P delta effects, what happens to the stiffness matrix? When we consider P delta effect, we have the matrix, the usual matrix, you know, 12 EI by L cube, okay, 6 EI by L square. The usual matrix, you remember? And when we consider P delta effects, we get P by L, or if I do it plus, so minus P by L, okay, 0, P by L, 0, 0, P by L, 0. So this is our KG matrix. You remember how we obtained this? You can look into it. But when we consider P, then the stiffness reduces. So this is our KG matrix. Now how to yes?
This is over elastic KE because
This is KE.
KE.
This is KE for a member. This is KG. Okay, and it depends upon P. I told you that it depends on delta. Is it depending on delta?
Yes, sir.
How?
Actually, when the delta is increasing, then the effect of the delta is also increasing.
But how in this matrix delta is coming into picture? The P itself depends on delta. The vertical axial force in my member, that depends on delta, isn't it? So when you are displacing the structure more, okay, the axial force is increasing. In one side column it is reducing in the other side column. So the P itself is function of delta displacement. Okay, so that's how this becomes a function of delta. Okay. Now in case of material nonlinearity, how this will come into picture? What will be the stiffness matrix taking into account material nonlinearity? If I have to develop matrix, okay, for let us say any member, frame member, what are the steps? How we develop stiffness matrix? One way is by solving the equations as I have told you. Another is finite element formulation. So do you recall the finite element formulation for stiffness matrix? How the stiffness matrix is obtained in finite element formulation? Anybody? All of you have done course of finite element mathematics. So how this is obtained? This is the most fundamental relationship used in finite element. B transpose you recall this? That's how the stiffness matrix is obtained. What is E or D matrix? Sometimes we also use D here. What is this matrix? Give me that. Constitutive relation. So, what is meant by constitutive relation? The relationship between stress and strain. So, if the material has yielded, let us say we are considering a perfectly elastic, perfectly plastic material. This is our material. Okay. What will be the value of E till this strain? It is linear elastic. Okay, so E will be same. What will be the value of E after this? 0. So value of E, this matrix is function of strain, and strain is function of displacement. So at different displacement, this will be value. So you have to constitute the stiffness matrix at different displacements. Okay, corresponding to those displacements you will get the strain. Corresponding to those strain you will get E, and then you will develop the stiffness matrix at that stage. Okay, that's why in nonlinear analysis it takes a lot of time. The computational effort increases because in case of linear analysis, to develop the stiffness matrix only once, and same stiffness matrix you continue to use. In case of nonlinear analysis, at every step you have to constitute the stiffness matrix. Okay, and that stiffness matrix you will use here in the convention. Okay. So the problem here is that this KT is no more constant. this also varies with depth due to geometric effects, due to material. So how to solve such system of equations? Okay. There are two methods available. Okay, the first method, which we call non-iterative. Method. This is also called simple step. Okay, so what we do here, at any step, this delta I, this is equal to delta I minus 1 plus d delta I. D delta I is the incremental displacement. Okay, and k bar I into d delta I, that is equal to dq. So here this dq I, this is incremental force. I have increased the load by an increment dq. Okay, due to that, the displacement will increase by d delta, and I have to simply add those what I have got in the previous step. Okay, and what is done here is this ki bar. What is this ki bar representing? Ki bar is representing the tangential or stiffness within the increment. But the problem is that the stiffness within the increment is also not constant. Here also you have seen that actually within this increment also stiffness has changed. It is not constant. So which stiffness I should take? Earlier I have told you that I will take tangential stiffness here. If I take tangential stiffness here at this point, it will be inaccurate here. So I can't get this point by considering this stiffness. Can I get? What displacement I am going to get? Let me draw it in more detail. The actual curve is, let us say, actual behavior is like this. I am trying to obtain this. This is my qi minus 1 and this is qi. And this difference between these two, this is dqi. Corresponding displacements are here, and this is d delta. This is delta I minus 1 and this is delta. Now here, up till this point, somehow I have completed my analysis. This point is known to me. Now I want to calculate this point. How I will calculate? One thing is that you take, one option is that you take a tangential stiffness. If I do this tangential stiffness and calculate this displacement for this dqi, actually I am going to get this displacement, not this one. Okay, so the problem is that this ki cap is also not constant. Okay, so I have to get a constant value. So what people have suggested, the wise people, they suggested that let us take this ki as summation of alpha j kj, and j is equal to 1 to n. What is this kj? Calculate stiffness, tangential stiffness at several points in between. So calculate tangential stiffness here also, get this kj, and this kj. So get tangential stiffness at several points in between. Okay, and use weighted average. What is alpha j? Alpha j is weight of different point stiffnesses. So whatever stiffnesses you have got in between, that you take some average, some sort of average stiffness, okay, and use that depending on what stiffness you are considering, how close it is to reality, that will give you this point. Suppose you are considering this stiffness, you can see that you will get exactly the same point.
So in between I minus 1 to I, we have a certain number of substeps there,
Right.
and we have calculated the stiffness modified each step,
Right.
each substep.
Right. Yes.
If I reduce the step size so that
If I reduce the step size,
then I can repeat as linear. When
I am coming to that. That is a special condition, and that method is known as Euler method. So, what Euler has suggested, that let us use j equal to 1 and alpha j also equal to 1. So in that case, what will be this ki bar? Okay, so alpha j is 1 and kj is also 1. So this ki will be equal to 1 into kj. That means the tangential stiffness calculated at the first point. Sorry, j is 1. Okay, so this is Euler method. In Euler method, what you are doing? Let us say this is our actual curve, load displacement behavior, which we are trying to obtain. So what you do? First you will take this tangent. You will calculate the displacement at this q1. Then what will happen? You will consider this tangent So slope will be of that tangent, but starting point is here. That will give you the second point. Then you will get the stiffness here. That will give you the third point, and so on. So this is actual and this is computed behavior.
What is this difference with respect to the previous stiffness?
Sorry?
What is the difference you are taking?
The stiffness is, this is nothing but the slope here. The slope which you will have, this slope will be same as this. So at this force, whatever
So
slope
the
you are
reference line
having.
is the previous stiffness path.
Sorry?
Previous stiffness path and the previous like what are the stiffness?
The initial point at every step, this is our first point, this is our second point.
Yes.
For the ith increment, this is first point, this is second point. So I am taking K1, the stiffness at this point, to calculate the displacement here. So tangential stiffness at the first point. Actually the tangential stiffness between this is also changing. No? So I am considering whatever is at the first point. That is the Euler's method. Okay. It is simple because here you have to first calculate displacement at given force using initial stiffness, then calculate the displacement there. At that displacement, you calculate the stiffness of your structure, which will come from come from the nonlinear relationship, taking into account geometric and mathematical nonlinearities. That will give you a slope. Use that slope to obtain the second point. Then this will give you another displacement. Now at that displacement, you will calculate the third stiffness, and so on.
Sir, but how do we get that means that the second slope?
Second slope.
Yeah.
Second slope is nothing but the stiffness, isn't
Yes,
it?
sir. Yes.
And I told you the method to develop stiffness matrix corresponding to a given displacement. Means taking the P delta effects at the displacement and taking the strain or E matrix at that stiffness, at that displacement. You know the displacement?
Yes.
From the displacement you can get strain.
Yes.
From the stress strain behavior you will get the value of E.
Yes.
Use that value of E, you will get the stiffness matrix at that displacement.
Okay. So I get this stiffness at particular displacement point.
Right.
So after that, how do I look at till which point this stiffness is valid or not?
See, I have this Q here. Q I will divide into different small segments. I will take the first segment of Q. I will calculate the displacement at the end of that first segment.
Yes.
I can calculate. Now I know the displacement here.
Yes.
At this displacement, I will get the slope
Yes.
from stiffness matrix. I will use that slope from here onwards to get this point. Now I will get this displacement. I can calculate the stiffness at this point. That displacement that I will use to get this point, and so on. Okay? Is this clear?
Sir, it is okay, but that method is more accurate than
Which method is more accurate?
No accurate.
Both are same.
No, sir.
I have talked till now, I have talked only one method. I have not talked any other method.
No, but the computed graph is deflecting from the actual graph.
Yes.
But
Yes, it will deflect.
Yes.
It will deflect because the stiffness which you are calculating, actually you should calculate this stiffness.
Yes.
But you are not calculating this, you are considering this stiffness.
Yes. Right.
So it has to deflect.
Sir, but in some step, we decompose now that the error, the divergent error.
Where I have calculated error.
Sir, in some step, that means that we have calculated only this. As more this. So we have convert it to the substep to minimize this effect. To minimize this
But
reduce.
in Euler method, I am considering only one substep.
So that's why the Euler method is less
Accurate.
accurate. That's why we are saying
What is the
non-accurate. You are saying that we are not.
So Euler method is non-iterative method and that too the simplest non-iterative method. I have not just talked about other methods. So it is the simplest method. Okay, using the simplest method also you can analyze. But as you have rightly pointed out that there can be a divergence from the actual behavior. Okay, how to take care of this divergence? What our friend suggested, keep the steps very small. Okay, so that the stiffness which you are calculating using a displacement at the initial point of that step, that is very close to this. The difference between this and this is small.
How much small? How much small? How to decide that?
There is no guideline. You have to decide. You have to check by try. Okay, you have to do that.
But how can I know that that is I am going for it by taking this much size?
I will come to that. Okay. So this is one of the methods where you can solve it easily, but approximately. So in Euler method, we are considering only one step.
Sir,
Yes.
basically this is the Q delta curve we have plotted for the any medium before this.
This is
Before midterm we have plotted Q delta curve, capacity curve for building by combining percentage. This is the this curve we are talking about this.
that was a simple method. What I have taught you before the midterm exam, that was a simple method suitable for hand calculations to give you an insight into what is happening in a structure. Okay, but in reality, you will not do like that. I told you. In reality, you will use a computer analysis and which will be following this procedure, one of these procedures. Okay, so
But sir, if I know the maximum values of the displacement and the Q,
maximum value of displacement and Q, how do you know?
I have calculated in
How?
capacity curve.
From where do you get the capacity?
I have calculated manually. Before midterm we have
Manually you can solve simple problems, and that too approximately. You can't solve a 40-story building having 10 columns this side, 8 columns this side. You can't do it manually. Okay, you have to use a computer model, and that too is very approximate. What you are doing manually is very approximate. I have taught you the manual method so that you get a feel of what is happening. If I start doing like this in the first class, will you follow anything?
Means same curve we have to plot by using only these methods.
Same curve we are trying to obtain using this method. Because here, computer is idiot. We can ask him to do anything. Okay. He will go on doing whatever we are telling. He will go on doing. Okay. So we have to develop an algorithm in which, if it has to do repeatedly the calculations, it should give me more accurate results. So we are trying to obtain those methods in which I can go on increasing the accuracy of my method. So Euler method is the simplest method, which is very close to our manual method, which we have done. It is simple, but at the same time, it is less accurate. How can I increase the accuracy? One method I can do is, one way of increasing this accuracy is that let's increase the value of m. So we have what we call second order there was one method, one more method, Ralston method. Okay, let's do Rangaputta only. So second order Rangaputta. In Runge-Kutta method, we obtain this Ki as alpha times K1, alpha 1 times K1 plus alpha 2 times K1. Okay. So earlier we have taken it only as K1, initial tangential stiffness. It is taking initial tangential stiffness plus another point in between. Okay, so one more point it is taking in between, and then this equation is solved as Ki d del mu equal to mu Qi, okay, and 0 is less than mu is less than 1. That means anyway somewhere in between I am taking the second point, not the final point. In extreme case when mu is equal to 1, it will be the final point. Okay, so somewhere in between I am taking that, and delta 2 is nothing but delta I minus 1 plus d del mu. So what is this del mu? Del mu is some displacement within that increment. Okay, delta I minus 1 is what? The displacement at the start of that increment, and delta I is at the end of the increment. Mu times dqi I take. Okay, dqi is the increment, mu times of that I take, and then I solve this equation to get d del mu, or in other words, between the increment I am taking some substeps to solve. Okay.
Possible only when the dq terms is linear. Variation in between the differentiate I to
No, it is not linear.
the equation.
If it is linear, then we need not to solve it. There is no need to solve this equation. We can get from simple proportionality. So we are not obtaining this d del mu, okay, from proportionality. Otherwise it will be simply mu times d del I. So d del mu is not equal to mu times d del I. Okay, if it was this equal to, then what you are saying is correct, that it was linear. So we are considering the nonlinearity of stiffness in between also. Okay, so in this category there are two methods. One is what we call midpoint Yogendra method, where mu is equal to 1 by 2 and alpha 1 and alpha 2 is equal to 1 by 2. Okay, so in the middle of that star we are having another substar. Okay, we are solving our equation at that star also, and then the stiffness we will take as weighted average of the stiffness at the first point and the mid. Okay, there is another method in this category, what we call Ralston method. In Ralston method, mu is taken as 0.75. You will understand the stiffness is changing. We are taking the initial point and mid point, still we are not correct. If we take initial point and the point closer to the second point. Okay, and we gave the weightage to the second point also higher. It will be more accurate. So mu is equal to 0.75, alpha is equal to 1 by 3, sorry, alpha 1 is equal to 1 by 3 and alpha 2 is equal to 2 by 3. So all this mathematical jugglery, why we are doing? So that we can get the displacement corresponding to different values of qi, okay, as accurately as possible. Okay, but in all these methods of simple iteration, which I have given, these three methods, I have given you Euler, midpoint Ramaputta and Razi. There is one problem, that we do not check equilibrium at different steps. Equilibrium is not checked, and that's why there are chances of diverging from the two solutions, because we are not checking the equilibrium. Equilibrium has to be satisfied. I told you that three conditions have to be satisfied: equilibrium, compatibility, and so here constitutive law is satisfied. Do you agree? How? By developing the stiffness matrix at a given displacement. So we have developed stiffness matrix at a given displacement. We have used that stiffness to obtain the second displacement, but we never checked that whether there was any unbalanced. Where did I plot that well? Okay, let me plot it again. Yeah, here. So we have never checked that at this displacement I have calculated the stiffness, but whether this point is here or not, this I have not checked. How can I check this? Actually, at this displacement, I should calculate how much force my structure can take. So this is unbalanced force, Ri. This unbalanced force I have not checked. That is what I have with this one. These are simpler, okay, but divergence is possible. I have to keep the step size sufficiently small so that this Ri is small.
How we can consider the Ri effect in mathematics?
I am coming to that. There is a second category of methods which we call iterative methods. In iterative methods, equilibrium is satisfied iteratively. These methods are also called multi-step methods. Within an increment, number of steps, number of iterations are followed. What we do there is, I will just explain you how it works. Let's not go into the mathematical equations that may. This is the actual behavior which is not known to us. See, I am just plotting it in everywhere, but actually it is not known. If it was known, I don't need anything else. So this actual behavior is not known. Suppose at one step, this solution is known. At one step it is known. I want to be looking at the other step. Okay. So let us say this is my DQI. Okay. So what I can do is I can take the initial tangent stiffness or rather tangent stiffness at the starting point of this step, and I can solve it for this dqi, and when I solve it for dqi I will get some displacement. Okay, this displacement I will get, but you can see that the forces I will get at this displacement from my structure, there will be unbalance. So this is Ri. Okay, this is my first one. Then what I will do? I will now at this displacement I will get the tangential stiffness, and I will solve it again. Okay, so new tangential stiffness I have taken from this point. Okay, I have considered this Ri also, the unbalanced force also. Okay, and I have again solved. So this time for the same force I will get two. Again this much unbalanced force will be there. I will draw another tangent, again solve it, then again till this Ri is sufficiently small. It will never be zero because it is an iterative solution, but you can go on reducing in successive manner. Okay, so what you have to do? You have to develop your stiffness matrix first here. Then you will calculate this displacement by solving the equation, usual solution what we do. Then you can calculate, you can develop at that displacement, you can develop the stiffness matrix, and then you can calculate the internal forces. Internal forces you will compare with the forces which you are getting from, or this applied force which you have there. The difference will be Ri. Okay. Then you will subtract that Ri from that force. It will give you this force. Draw the new, use the new stiffness matrix. Okay. So this is ideal. Actually, these methods are used, and here also number of methods.
Sir, for calculation of Ri, I need 2 points, upper point and lower point. Upper point I know from the initial tangent.
Upper point is already known to me because this is dqi I have chosen. Increment of the load I am choosing.
Yes.
So increment of the load is chosen. So this point is known to me. Okay.
Yes.
And this point I can obtain from the member forces of my structure. I know displacement. At that displacement I can get stiffness.
Yes.
And at that stiffness and that displacement I can get the forces. So one is the forces which my structure is registering, and another is the force which is being applied, and both will not match. Okay, both will be different. Those will match only if my solution is accurate. Okay, so whatever is that unbalanced force, I will consider that and analyze my structure further for that unbalance, and so on till this unbalanced force becomes zero. Lower curve is actual curve which is not known to me. Okay, but I can determine any point here because I have to calculate the stiffness here. Suppose this displacement I know, at that displacement I can calculate the stiffness and the member forces.
If I already know that points on the curve, then why I am doing all those things? If you know all the points on the curve.
can't get the curve. Okay, and this point will depend on this point. I can calculate this point accurately only if this point is known to me. Incrementally, I can calculate these points. Okay, not in totality.
So what calculation of
Because in nonlinear analysis, the forces at any strain depend on the forces at the previous strain. So if this is known to me, then I can calculate these points. Okay. So I just wanted to give you an idea that how these analyses are done in computer software. Okay. So what we have done in the class is manual method. It is approximate method. It gives you insight how it is done, but numerically these equations are solved differently. Okay. So once you know what you are trying to achieve, then you can develop an algorithm to solve it. Okay. Fortunately, I can't ask this in the exam. Okay. But if I ask you to write a program, then you have to understand it. You have to.
Sir, doubt is we are approximating the curve. How do we get the benchmark point on the lower curve? That's what he is asking.
Right. So, or this Ri, which we are
benchmark
getting.
point.
So, I know any displacement. Suppose the displacement is known. At this displacement, I can calculate internal forces in my structure.
Okay, in terms of stresses.
In terms of different stresses, different nodal forces, then combining those, I will get the forces in terms of those nodes where the load is being applied. Because load is being applied at few nodes.
Yes.
Okay. Actual number of nodes is much larger. Displacement is known at each node.
Yes.
So when we know this displacement, we know displacement actually at each node. Not only at those nodes where force is applied. So by knowing the displacement, I have to calculate the internal forces in my structure.
So for particular displacement, we need to calculate the member forces. And for those member forces at a particular location, we need to somehow arrange them in an assembly.
Right.
And for that, we get the, by that we will get the
So that means first we will x-axis will divide into some number of steps, delta of 0.02, 0.04, like that, and corresponding
The
to
force
that
axis here. So this axis you will divide into number of steps.
number of steps corresponding to that.
And within each step, you will follow this. This I know.
Implicit for the further step we have calculated. In between sub step it is implicit method.
Implicit comes in terms of time step. This is not time step.
But we can
This is force step. So if you are talking about, let us say, Euler method, okay, so that is axis. That doesn't need. But these iterative methods, you can call that these are in. Here also, we don't need the. We are not involving the final step. We are proceeding from here only.
yes.
I don't know whether these are classified as explicit or implicit or okay. Implicit and explicit usually we talk in terms of time margins.
Just time margin.
So in time margin scheme and in real earthquake analysis, you have to do this at every time step.
Every time.
So at every time step, you have to take different steps of the load. So this is taking into account the non-linearity. Okay, not the variation with respect to time. So this combined with the variation with respect to time, that will give you the time solution. Okay, so that involves not only this but the time. For that there is another numerical scheme, another source of error. that is also approximate. That's why the numerically obtained nonlinear time history analysis results are difficult to interpret, and the chances of error are much more. And it is suggested never go for nonlinear time history analysis from the beginning. First do a linear analysis, then do a nonlinear static analysis. This is nonlinear static analysis. So do a nonlinear static analysis, then go for dynamic, nonlinear dynamic analysis. So that is nonlinear time history.
Actually, what we have to do within the time span, we have bounded our errors.
Time span will be bounded over.
With local fractions error in each time step, we have to minimize it.
Yeah, but how here you can at least satisfy equilibrium. So you have some benchmark to satisfy equilibrium. But in time marking you don't have any benchmark. So if there is error here, this error will go on accumulating in different times. So that also will.
We have time marking, we have nitrate testing, we have
Hybrid testing we are not talking. We are talking here that the properties of the system are known and we are trying to estimate its response numerically. Okay, so generally this we are not teaching here because it may become too abstract for you. That approximate method, okay, although it is suitable only for manual calculation, but it gives you a lot of insight. Here it is difficult to visualize what is happening until unless you write the computer program yourself. But you should be aware, because if you have to use the computer program which is commercially available, let us say ETABS or SAP you are using, it will ask you a few things. How many number of steps, how many iterations. So you should be aware which iterations it is talking about. So it is talking about these iterations. How many what is the maximum number of iterations which you are doing at each step. So you should be clear about those things which you will be using. So my idea was to give you an overview of how it is actually solved in a computer. Okay. So if you want to go for PhD, then we are planning that we will have a pre-PhD course where we will go into the details of these methods. You will be writing your own code, but for IMTech people who will be using some commercial available software, this much is added. Okay. If you want to read more details about it, it is available in number of books. MacWire book is available. KJ Barthe finite element book is available. Okay, and Chopra's book also is available. KJ Chopra's book also. Yes.